Hello, this is Jeff Hamrick again at the University of San Francisco's Financial Analysis program. I'm going to talk for a few minutes about an alternative to the classical Durbin-Watson test called the Breusch-Godfrey test. There are two advantages to using the Breusch-Godfrey test instead of the classical Durbin-Watson test. One advantage is that the classical Durbin-Watson test relies fairly heavily upon the assumption that the residuals are normally distributed, and the Breusch-Godfrey test is less sensitive to that assumption. The other advantage of the Breusch-Godfrey test is that it allows us to test for serial correlation through a number of lags besides just one lag. So that is to say, the Durbin-Watson test focuses on the correlation between a residual at time t and a residual at time t minus 1, whereas the Breusch-Godfrey test uses all of the correlations between the residuals between time t and time t minus k, where k is the number of lags that you've specified. If k is chosen to be equal to 1, then the Breusch-Godfrey test with one lag is very similar to the Durbin-Watson test, the classical Durbin-Watson test. But for a variety of reasons, certain econometricians and statisticians prefer the Breusch-Godfrey test as opposed to the classical Durbin-Watson test. So let me go ahead and import a set of data that we've used on a number of occasions in this class. This will be the set of data related to the monthly electricity bill of a family in Indiana. And I need to create a generic time variable, as usual, and then declare this to be a time series data set. And let's suppose that I create a regression model in which I regress the amount of the bill in dollars against, let's say, the average temperature seen that month, number of family members, an indicator variable as to whether or not there's a new electricity meter installed on the home, and two similar indicator variables related to whether or not a new heat pump has been installed on the home. I can go on ahead and obtain OLS estimates for the regression coefficients in such a model, but it's very likely, because this model is serial through time, that is, it's month by month by month data, it's very likely that the residuals in this model are subject to serial correlation. And as we've learned, that creates problems. For example, positive serial correlation in the errors tends to bias the standard errors of the regression coefficients downwards and inflates the student t-test statistics associated with those regression coefficients upwards. So rather than use the classical Durbin-Watson test, we can use the Breusch-Godfrey test instead. And so the way you would operationalize that is to use the command estat bgodfrey, and this is going to require a lag option to be specified. I'll choose lag 1 since that's the most similar to the classical Durbin-Watson test. And what you end up obtaining is a chi-squared statistic where the number of degrees of freedom of that chi-squared statistic is related to the total number of lags that were analyzed. Since I'm only analyzing the correlations, the autocorrelations of the residuals at lag 1, this is a chi-squared statistic with 1 degree of freedom, and it has a value of 30.251, which is very large, and the p-value is very small, so we would reject the null hypothesis of no serial correlation at lag 1 in the residuals. That's going to be confirmatory or agree with the classical Durbin-Watson test in this case. A nice thing about the Breusch-Godfrey test is that we can extend it a little bit. So if I wanted to study lags over the past 12 months, that is the lags, the correlation between the residual at time t and t minus 1, and the correlation between the residual at time t and t minus 2, and the correlation between residuals at time t and t minus 3, and so on and so forth, all the way down to t minus 12, I would use this command right here. That's a sensible approach in this case, since this is monthly data, and I have every reason to suspect that electricity bills are seasonal across years or 12-month periods. So if I execute the test in this case, now what I have is 12 lags that have been studied at the same time. So I obtain a chi-squared statistic with 12 degrees of freedom. I still have a very large chi-squared value for that Breusch-Godfrey test statistic, and my p-value is still very small, so I'm going to reject the null hypothesis of no serial correlation. So some sort of modification to this model is needed to address the problem of serial correlation. One approach would be to add in a lagged version of the dependent variable as an independent variable, in which case the Durbin-Watson classical test cannot be used. Other alternatives would be to study differences in subsequent values of our variables rather than the actual levels of those variables. That sometimes fixes the problem of serial correlation. And then there's also a way to adjust the standard errors so that they are less biased than is typically the case when you have serial correlation. We will perhaps talk about that with another screencast, but here you are, the Breusch-Godfrey test in state.